because we showed the shape functions of, we rederived the shape functions of a square element. And we showed that our n1x, just a minute, showed that our shape functions n2 x comma y is equals to a plus x b minus y n3 is a minus x b minus y, a plus x b plus y by 4ab, and n4 x comma y is a minus x b plus y by 4ab. And we showed that for any generic thing, the shape functions are obtained by choosing the basis function and evaluating this basis function at the coordinates, at the nodal coordinates, and inverting it would get you this capital A, and A is the evaluation of the basis at the nodal coordinates, and then inverting it and multiplying with the basis vector will give you the things. And second will only give you that the error would, there are other things in the two-dimensional finite element which are not there, are the compatibility issues. So we showed that for example, if you choose an element of two elements, this is element 1, element 2, the equation of this line is y is equals to mx plus c. So you have come up with estimation for the element 1, which is a0 plus a1x plus a2y plus a3xy, and for the element 2 is b0 plus b1x plus b2y plus b3xy. If you substitute y is equals to mx plus c in here and here, similarly in here and here, then you know that it will be you had 1 along the line L is given by a0 plus a1x plus a2x square, and for the element 2 is b0 plus b1x plus b2x square. Hence these two are quadratic, but we know values at only two nodes. Hence these two curves are non-unique, and hence what boundary is not guaranteed. In order to get over it, we need to go to the isoparametric state. So that isoparametric formulation would follow subsequently after a couple of classes. So or also known the rest of the procedure would remain same. So how to get over this, we'll explain when I deal with the natural coordinate system or isoparametric formulation. Now, so far what we have done is we have checked the completeness. This is for the completeness, and this is for the kind of compatibility, and for the convergence, if these two are satisfied, then your convergence will be guaranteed, and the convergence can be measured as, this is for an error. So for convergence, order of h to the power of p, that is nothing but it goes as c into h to the power of p, where c is your rate of convergence and this is order of convergence. Regarding the element libraries itself, but let's not waste too much time and let's go into actual equilibrium equation. How do you solve those things? So later what I did is given by sigma 11, sigma 12, sigma 22 symmetric because of angular momentum balance being satisfied by default for non for materials with no body moments. Similarly, this is for the 2D. For the 3D, sigma would be sigma 11, sigma 12, sigma 13, sigma 22, sigma 23, and sigma 33, this being symmetric. Now, in the similar manner, our strain is also there. Let's start with the strain. Strain is epsilon 11, epsilon 22, and the symmetric part of it. And for this case, it is epsilon 11, epsilon 12. This is for the 3D. Epsilon 13, epsilon 22, epsilon 23, epsilon 33. This being symmetric. This symmetry is because of some other reason. This symmetry is by definition, that is, for small strain, the epsilon ij is given by 1/2 of ui comma j plus uj comma I. That is, since the quadratic terms are neglected from the finite strain part, the small strain, this gets interchanged. So if I interchange it, so this would be uj comma I plus ui comma j. That means it is epsilon ji. So this is by definition itself, this is symmetric. Whereas the stress is symmetric because of the satisfaction of the angular momentum balance for for the materials with no body moments that are present in the system. Okay, now let us go further down, and what we did was we used our numerical approximation, which is u tilde is equals to ui ni, which is a function of x and y, as I showed in the earlier case. Now what we do is, similarly, my v displacement is vi ni x comma y. So we showed that epsilon 1 1 is can be written as u1 to, let me write it in a summation form, that is, it is dou u by du by dx or dou u by dou x because it is partial. So what we did was dou by dou x ui ni x comma y. So this has become u1 dou n1 by dou x plus u2 dou n2 by dou x plus u3 dou n3 by dou x plus u4 dou n4 by dou x. Similarly, epsilon 2 2 was dou v by dou y. This has happened to be v1 dou n1 by dou y plus v2 dou n2 by dou y plus v3 dou n3 by dou y plus v4 dou n4, and epsilon 1 2 So this would be, I'm sorry about that. So 1/2 dou u by dou y plus dou u by dou v by dou x. So that is given by dou y x plus u2 dou n2 dou x dou y plus v2 dou n2 by dou x plus u3 dou n3 by dou y plus v3 dou n3 by dou x plus u4 dou n4 by dou y plus u4 dou n4 by dou y, with a half symbol that is present all over. So this, what we have done, we have written it as epsilon 1 1 epsilon 2 2 epsilon 1 2 as dou n1 by dou x 0 dou n2 by dou x 0 dou n3 by dou x 0 dou n4 by dou x 0. 0 dou n1 by dou y, 0 dou n1 by dou n2 by dou y, 0 dou n3 by dou y, 0 dou n4 by n1 by dou y, 1/2 dou n1 dou x, 1/2 dou n2 dou y, 1/2 dou n2 dou x, 1/2 dou n3 dou y, 1/2 dou n3 dou x, 1/2 dou n4 dou y, 1/2 dou n4 dou x times u1 v1 u2 v2 u3 v3 u4 v4. So this is a quite an important thing which we have done. The epsilon vector is given by B matrix times the degree of freedoms. So this is called strain displacement matrix, and this relationship is called strain displacement relationship. So it is clear that if you know the degree of freedom for the nodes for an element, the degrees of freedoms are u1 v1 u2 v2 u3 v3 u4 v4. So which is nothing but your degree of freedom d1 d2 d3 d4 d5 d6 d7 d8. So all the degrees of freedom, if you know these things, the strain inside anywhere is obtained by multiplying with the strain displacement matrix. So this was the important thing that we have derived in the last class. Now after this, what in the today's class what we will do is we will give the stress strain relationship. Before that, let me just break for a couple of minutes, and let me just check if you have any questions. Choice of x. The choice of x can be, is it like x to the power of 5, x to the power of 10, x7, x19, something like that, or it should be 1x. Sorry, I will do it for the two-dimensional state, not one-dimensional state. So for the two-dimensional state, we should write it as x 5 x y square x to the power of 3 y y to the power of 5, or I should take it as this is choice 1. The choice 2 is x square y, x square y square, y square x to the power of 10, y to the power of 10, or choice 3 is 1 x y x y. Out of all these things, this choice is not good, this choice is not good, whereas this choice is good. Why? Because how many nodes are there? We have 4 nodes. If it is 4 nodes, what I will take is, I'll take this red color things, a 4-noded triangle. So I'll take 4-noded triangle. The 4-noded triangle is, I have to take 1 x, x, y, and y. Any combination of this, see, the choice of all the elements lying within this box will give you the best possible choice of your basis function. If this basis function is chosen in this thing, then this is complete. What is the completeness? This is complete up to h to the power of 1. Let us check it out. So quantity, any quantity is nothing but phi tilde plus order of h to the power of p. Now in the universal set is 1 x y x square x y x square, sorry, y square, like that. Everything in this Pascal triangle would be your universal things. But out of that, if you choose these things, then your linear in the x has been taken, linear in the y has been taken, and xy term is also a linear in x as well as linear in, so it's kind of a linear in both x and y. So this is linear term, this is linear term, and this is linear term. So if you take all these things, instead of picking x square or y square for the fourth thing, what you are taking is any linear variation within the things is been taken by your approximation. So your p has to be 2. So here p is equals to 2 for your case, because any quadratic, all the quadratic terms are left. X square, y square, this is more than x square. Anyway, this has a linearity in y, that's it's a secondary, but in x square it has been taken, and so on and so forth. So this guy is kind of very good in kind of taking it. If you want to choose a best complete polynomial for a 4-noded triangle, 4-noded or a 9-noded or anything, you try to, if it is a square, what I would suggest is a quad, you try to take it in this direction. You make a square picture on this triangle, then you'll get all the ingredients of the basis function, which will be close to the completeness up to certain degree. Okay, this would be to complete up to the first one, so the p2 will be gone to the second guy. Now for the triangle, Pascal triangle, whatever is the shape of the triangle on the top half, top things would give you a complete polynomial for the choice of 3-noded triangle or a 6-noded triangle. So if I have to choose basis function for a 3-noded triangle, then I would choose 1, x and y as my basis function. If I have to choose a basis function for 6-noded triangle, then I would choose 1 and then x square, xy and y square. This would be complete up to the second order, because all the linear terms has been taken care here, and then this is the second degree things. So the third will be left out with the error function. And if I have to take 9-noded, then I'll take entry of 1 xy, x square, xy, y square, not x cube, but x square y, xy square and x square y square if it is 9-noded element. For 4-noded element, I'll take 1 x, y and x into y. So this is the choice of things that will give you the completeness. If a function is complete, the error will behave in a manner that it will diminish with the increase in the with the decrease in the mesh size. So if the size of the mesh has to be decreased, for example, I will show you with respect to 1 dimension. If it is with respect to 1 dimension, so let's say temperature with respect times A0, A1, A2. Let's say this is my approximation. So T is an exact thing. Q. Because in the universal set, which is nothing but 1 x to the power of 1, x to the power of 2, so on x to the power of n, and n tends to infinity, I have picked all the minimum basic things. If I remove that, my error would have a basis which varies as x cube, x to the power of 4 all x to the power of n, and out of this, if I all these terms I can remove x cube common. If I remove x cube common, it will be so that means this whatever is the common factor I've taken, the highest power of that, right? This represents this p. That means now if mesh 1 has mesh size h and mesh 2 has mesh size h by 2 and mesh 3 has mesh size h by 3, this is the size, then your error would go as order of h to the power of 3 here, whereas this one is h by 2 whole to the power of 3, that is equals to 1/8. So it decreases as 1/8 of it. Similarly, if I take it here, then it will be so the error in this case and error in this case, if I fraction, the error in this is 8 times smaller, or it is diminishing much quickly, and if I take it here, it is diminishing by even more quickly because it has a factor of 1 by 27. So this, in order to have advantage with the decrease in the mesh size, if you want your error to vanish, then you should choose a complete polynomial. In order to choose a complete polynomial, what we are saying is you better go ahead and pick your choice from the Pascal's triangle. This is about the Pascal's triangle. Two-dimensional state of stress, there are two different reductions for the 2D from the 3D. When your sections are very thin, that comes under plane stress, and if the sections are very huge and bulkier like a dam sections, then it will come under plane strain condition, provided in both the cases the loading is along in the plane of 1 and 2. Okay, so with the in-plane loading, and what we can do is we can reduce the problem from 3D to 2D, and if it is a plane strain reduction, then your stress strain relationship is governed by this thing, and if it is a plane strain condition, then your stress strain relationship is governed by the following. Three sigma 1,3 is equals to 0, sigma 2,3 is equals to 0, epsilon 1,3 is equals to 0, epsilon 2,3 is equals to 0, but epsilon 3,3 is given by minus mu by E, sigma 1,1 plus sigma 2,2 is your things. In all the above things where capital E is Young's modulus and nu is Poisson's ratio. So now simply from now onwards, I'll try to write for plane stress, plane strain or plane stress. I can simply write my relation between my sigma and epsilon as a D matrix. So this guy is the D matrix for the, I'm sorry about that, I missed something here. Here I need to write strain vector epsilon 1 1, epsilon 2 2, epsilon 1 2, epsilon 1 1, epsilon 2 2, epsilon 1 2. So this guy is the D matrix for the plane strain, and this guy is the D matrix for the plane stress. So now we have plane stress condition. We have obtained first thing is stress strain relationship. Sorry, strain displacement relationship. And stress strain relationship. Now what we need to do is we need to solve our governing differential equation for the 2D structures. So in order to do that, we have several ways to come up with. First thing is what we have is our governing differential equation, which would be which is nothing but linear momentum balance, which simply says that del dot sigma plus b equals to 0. So the del dot sigma plus b can be written further as, if you want to do it in the initial notation, which is written as dou sigma ij by dou xi plus bi equals to 0. So, but further in 3D, this is for the 3D. For the 3D, it is given by dou sigma 1 1 by dou x1 plus dou sigma, sorry, this is xj, because this is free index is the thing, this is so this is sigma 1 2 by dou x2 plus dou sigma 1 3 by dou x3 plus the body force in the first direction, right? This is in the along one direction. This is the force equilibrium in the first direction. If I seek for the force equilibrium in the second direction, this would be sigma 2 1 by dou x1 dou sigma 2 2 by dou x2 plus dou sigma 2 3 divided by dou x3 plus b2 equals to 0. Similarly, the thing in the third direction would be dou sigma 3 1 by dou x1 plus dou sigma 3 2 by dou x2 plus dou sigma 3 3 by dou x3 plus b3. But if it is two-dimensional, then the second and third direction is by default satisfied, because as we saw earlier that for the plane stress or plane strain condition, sigma 1 3 sigma 2 3 equals to 0. Further, all our sigmas are not functions of x1 x2 x3, but it is only function of sigma x1 and x2. That means by default there is no variation in x3. That means even though whatever it is there, by default these two terms would be vanishing, and we know that these the other things are there. One can show that this condition by default accept in the other directions. So this is trivially satisfied in the second and third direction, but in the first direction only we need to consider if we are solving the 2D problem. So this is one way to start with our differential equation, but what we need to do is we need to take this differential equation and then develop so anyway, let me write down for 2D. The only thing that is under consideration is the first thing. So sorry, but not the only the third thing is irrelevant. The first two things are still relevant. Only these the third one is irrelevant. Because 3, 1, 3, 2 are gone here. This is still not. I'm sorry about that. I think so for the two-dimensional problem, we have still two equations that are under consideration. So we have this equation under consideration. This equation is under consideration. This equation is also under consideration, but this is trivially zero because sigma 3 is not a function of 0. So this is equals to 0. This is already equals to 0. This is equals to 0. And since there will be no body forces, this third equation is trivially satisfied, whereas first and second are not. And further, these terms are equals to 0. So we can write in our 2D scenario that the governing differential equation would be something like dou sigma 1 1 by dou x1 plus dou sigma 1 2 by dou x2 plus b1 and equals to 0 and dou sigma 2 1 by dou x1 plus dou sigma 2 2 by dou x2 plus b2 equals to 0. Since the stress is symmetric, I can rewrite this guy as 1 to itself. So this is our governing differential equation for 2D. The third one is trivially satisfied. So further, we need to have boundary conditions. So the boundary condition is equals to u is equals to u star on certain boundaries, and t is equals to t star, that is on gamma t. This is displacement specified. This is traction specified. So these are the boundary conditions that which will be there. So now what we need to take is as we already know that in finite element methods, we cannot start with a strong form because governing differential equation is also known as the strong form. We need to develop the weak form. The weak form we can develop it by taking in several different ways. Starting with the governing differential equation as it is would really pose little bit difficulties in solving the thing. So what I will do is I'll propose something called as principle of virtual work. Okay, so in the principle of virtual work, what we do is we define a kinematically admissible virtual function. So we introduce principle of virtual work where our virtual displacement is given as delta v, where it has to be kinematically a thing is called kinematically admissible if the v of x is equals to 0 on gamma u. So gamma u is on the boundary where u is equals to u star, your v has to go to the 0. And here when I say v is a vector with which it is v1 is the in the one direction, v2 in the third direction. Anyway, I'm doing 2D, so if it is 3D, it will also have 3 dimensions. So it is like x, y, z directions. It is, this v is not the displacement in the y direction, it is a displacement vector, and this is a virtual displacement. So, and we take this such kind of a displacement, sorry, delta v of x, such that it is equals to the thing. Okay, so this is the kinematically admissible thing, and in that case our virtual strain would look like something like this. Is our kinematic is our virtual strain. Then we define the principle of virtual work as the internal work done, or the internal energy stored by the structure on the application of this virtual displacement is equal to the external work done by the virtual displacement, that is energy balance. So what I will do is, the energy is sigma ij epsilon ij, sorry, on a omega. So let me show the problem. So this is your omega, p is equals to, sorry, this is constraints. So u is equals to u star on this gamma u boundary, and somewhere here this boundary is t is equals to t star on gamma t. And further you need to understand that gamma u plus gamma t is equals to total gamma. This is nothing but total surface or boundary, and this is domain. And within this domain, what we are saying is it satisfies del dot sigma plus p is equals to 0. And we have mentioned u here, traction somewhere here, and then we are saying that sigma is equals to, I mean, in terms of initial nut, the thing, the Hooke's law can be written as c is equals to c epsilon, or in terms of the thing, what we have written is our constitutive law is sigma is equals to d times epsilon. It is a similar relationship written in a different style. This is in a tensorial form and this is in kind of vectorial form. So given this material, this is the Cowning differential equation within this domain, and saying that this along this boundary it is this boundary is constrained, and along certain boundary this is loaded. Then what is our displacement, what is our strain, and what is our sigma inside inside each and every point in the boundary. So this is our question. The question for us is, what is the u, epsilon, and sigma all within the structure, provided it has this constraint and that constraint. So what we did was, and further we said that gamma u plus gamma t is equals to gamma. That means you need to understand that here all these places there is no traction. This is also called as traction free. So the traction free is also known as t is equals to T star, which is nothing but 0. Where the traction is not specified, you take traction as 0. So this part alone is gamma u. This alone is gamma u, and the rest of the part, including this thing, is gamma t. So this is gamma t, and this is gamma u, that is equals to entire thing. And even though there is nothing specified here, that is traction free, so you take T star is equals to 0. If T star is non-zero, there will be a physical force that will be applied, otherwise the physical force is 0. That is what you need to apply as your boundary conditions. So anyway, so we'll come back to this problem. For the same problem, what I'm saying is I have certain virtual displacement dV on this thing. This virtual displacement which have such that because of this dV is such that at this place my dV was equals to 0. That is the only consideration on this boundary gamma u. Then my virtual strain is given by this thing, and because pulling it by this virtual displacement, the internal energy stored in this structure is given by this one, and the external applied load on the body forces which are present would give the external work done is given by on the surface gamma t so the internal work done or internal energy stored is equals to the work done by the external forces, or if I bring it to every one side with a negative sign, internal energy minus external work done has to equate to 0. So the differential work, the virtual displacement says that any differential internal, it is nothing but the energy balance, the amount of work put on this is totally stored as the internal energy of the system. That is what is called principle of virtual work. And using this principle of virtual work, what we'll do is, this is already is in the weak form. We'll try to develop something called as our finite element framework. The principle of virtual work itself is your integral form, or what do you call it as weak form. One can show that this weak form is very much equivalent to the strong form or governing differential equation, but I would not try to prove it in the today's class. You can come up from the principle of virtual you take your governing differential equation and then you multiply with respect to the virtual displacement, and then you carry out some kind of divergence theorem. Then you can write it in the similar form for certain quantities, and all the things that you have been using is nothing but method of weighted residuals and some divergence theorem that you can do it. But I directly write it with respect to principle of virtual work, which is nothing but this one. And this is our starting point of our finite element methods, because finite element method starts from the integral form, and this integral form is quite an essential to go forward in the finite element sense. So at this point of time, what I will do is I'll take a break and I will ask if you guys have any questions. Otherwise, we'll continue. We have I and J going from 1, 2, and 3. For 2D FEM, I comma j takes from 1 and 2. So the same thing would hold true, only that the I and j are restricted only to 1 and 2. So the same equation holds true. So sigma ij epsilon ij dv0 minus omega bi. So let me rewrite this guy. We know that our virtual displacement is this one, but I want to approximate it. So our approximation for the virtual displacement is given by delta Vx, and that is given by what I would call it as delta Vi Ni, very similar to, so very similar to what we used to have for the so this is your vector. So this vector would look like, so this one is n1 0, n2 0, n3 0, n4 0, 0, n1 0, n2 0, n3 0, n4 delta v1. This is delta. See, there are two things. One is your u displacement and v displacement. So when I write these things, anything in the subscript is one direction and two direction, and anything on the top is what I will write it as node number. Unlike so unlike what we have used to have notation in 1D, because we have two things that is coming up in the in the higher dimension is like we have direction as well as the node numbers running. So I would write it as dv1 dv1 2 for the node 1, and the first component for the node 2, the second component for the node 2, next the first component for the node 3, the second component for the node 3, next the first component for the node 4, and second component for the node 4. So this is our thing. So this is our virtual displacement, and our original displacement is also given as u bar. U tilde of x can be written as in the same manner: n1 0, n2 0, n3 0, n4 0, 0 n1 0 n2 0 n3 0 n4. This is u1 node 1, u2 node 1, u1 node 2, u2 node 2, u1 node 3, u2 node 3, u1 node 4, u4 node 4. So that I can write it simply, if you want to understand, as the first component which is approximation is written as ni, and let me call it as na a. So the summation is over the A, and A runs from 1 to 4. So that is nothing but n1 1 plus n2 first component for that thing, n3 the x direction for the third one, and n4 u. Similarly, this is I can make it generic by writing it as I. So the same thing, if you want to write it in the matrix form, this is what is there. If I keep it, this is 1, then actually this can be written as a vector. This is nothing but u1 component, u2 component is nothing but this thing. So n1 u1 for the node 1, n2 u1 for the node 2 plus n3 for the node 3, and n4 for the node 4. Similarly, if we are doing for the second one, this would give the same thing. So unlike one dimensional, it's the same thing, but because of we rewrite it in little bit different form. So this I call it as capital N. So I simply write my shape functions u tilde of x as a very big N times u bars, because this is my degrees of freedom. So this is a better way to write it, my u tilde, which has this itself is a vector. It has the first direction and the second direction. In other alternate languages, we generally call it as u displacement and v displacement. Instead, I would prefer to call it as u1 and u2. Okay, so this is just a notational change, but there is nothing big difference. And similarly, what we have shown is our strain is given as B matrix times U. This is also we are clear, so which we have shown it earlier. So this is strain displacement matrix, this is shape function matrix, and this is the thing. And the same thing equally applies for our virtual displacement. So instead of use, these are virtual things. So, and virtual strain, so when I write capital X, this X, you also note that X is nothing but x1 e1 plus x2 e2. It is not simply the X. So I might have a little bit notational confusion, but I would like to take it in this manner so that we can easily handle our both the dimensionality and the summation symbol easily. So anyway, this is given by the strain displacement matrix, whichever is same, times delta V bar. So we use this definition, and further we know that our sigma is equals to d times epsilon. So, but this is for the exact. For the approximation, this would be the same as the approximation in the strain. The approximation in the strain, you take this definition and substitute in here. In that case, we can write sigma tilde is equals to d times b times u. Okay, so now I have my definition of stress, I have my definition of virtual strain, and all other things that are there. Now I'm in a better position to write this and simplify it. So before I do it, I rewrite my kind of this thing in a simplified fashion again. So the principle of virtual work is written as sigma ij epsilon I, sorry, bi delta vi dv naught gamma di delta vi dA naught. So this can be written as, this is nothing but a double contraction, so I can write this one as trace of, or simply sigma dv naught minus, this is delta v transpose b dv naught minus delta v transpose dot t. So now we have our approximation. When we put this our approximation in here, we can simplify it, but anyway it is our class time has ended. So what I will do is I will try to pursue it in the next class. Till that, if you have any questions, let me ask here, and then we'll continue in the next class.